Okay, YouTube, in this video we're going to be using our theorem for finding all the nth roots of complex numbers in trig form in order to solve equations of this type where we wanted to find all roots in the first place. So for instance, we have an equation x cubed plus 1 equals 0. What I want to do is I want to solve this and then graph the solutions. So now we know from experience if I wanted to solve an equation like this, it's a third degree polynomial. So I should get 3 answers here. Or at least we could say that when I solve this, I would subtract 1 from both sides. And then I would have to take the cube root of both sides. So we know this from our last video. If we take the cube root of something, there have to be exactly this many roots. Okay, this many roots. So one thing I want the audience to kind of consider is this. I mean, if we took the cube root of x cubed, we would just get this. We would just get x. And we say, well, the cube root of -1. What we're really asking is, what could I take times itself 3 times to get -1? The only number I can think of here is -1. So that's the thing. That's the only number I can think of because it's the only real answer to this. But what we have is there are actually 2 answers to this that are complex that do not pop out of this as real numbers. So what we're going to do instead is this. We're going to solve this equation exactly the same way, but I'm going to kind of list my steps over here and be really explicit in what it is that I intend to do. And that is this. If you have an equation like x cubed plus 1 equals 0, and we say, well, what we get is x cubed is equal to -1, and I want to solve this, okay? What we're going to do is we're going to take the cube root of both sides, but what I'd rather have be true is this. When I say that this is equal to the cube root of -1, we are going to interpret this as if it is in trig form, okay? So what we want to do is we want to rewrite this into trig form. Right now it's in standard. It's in standard. We're going to write this. It's in standard form. We want trig form. And the reason why is exactly this. Because if we were to take the nth root of a complex number in trig form, where z is equal to some r times cis of theta, what we know we get from this theorem is this. We get this. Instead, we'll write it as r cis theta to the 1 over n power, where we can now say that this is the r to the 1 over n times cis 1 over n times theta. And we'll talk about this 1 over n times theta when we get to it. But we say theta plus, and I really should say 360 degrees times k. Any coterminal angles here. But we get this. Okay, so what I want to do is I want to interpret this as being in standard form right now, which right now it is the number z. I don't want to call it z. Let's put it, I guess it is a complex number. We say z. We say -1 plus 0i. So if this is our number right here that we want to take the third root of, first thing I'm going to do is I'm going to go graph this. I'm going to say, what would this be in in trig form? So we'd say that -1 comma 0 would be this point right here. That's -1. We say, here's my vector. So we'd say that in trig form, we know 2 things about this. We know that the argument is 180 degrees, and we know that the r value right here, we could say r is just basically 1. Okay. And we could also say this, as a matter of fact, we could say that r is equal to the square root of, we have x squared plus y squared, but we just get 1. So we'll put 1. So this trig form of the number would be this. We'd say r is 1, and then we say cosine I sine 180 degrees. We just got that just from observation. Okay, so we say if this is my number right here, instead of taking the cube root of -1, what we're going to do is this. I'm going to kind of borrow some real estate over here. We say that x, which is equal to the cube root of -1, has to be then this. We say the cube root of, and our number here was this, 1 cis 180 degrees, because they meant the same thing. Furthermore, we say that x, is equal to 1 cis 180 degrees to the 1/3, and now what we can do is we can actually use our theorem, de Moivre's theorem. Okay, so we'd say, well, this would be x equals 1 to the 1/3 times cis, and here's the tricky part. We say, well, theta is the original angle. What we're going to do is we're going to take 1/3 times 180 here. So we'd say 1/3 times 180 is 60. In other words, what we could do is we could take this 180 and divide it by n, which in this case our n down here is that right there. N is 3. So we'd say plus now 360 degrees over n, and then we'll put the k off on the side. And perhaps I should call this right now, we should just call this the original angle 180 degrees divided by n, which in this case is 3. Okay, and we get 60. So now when I simplify this, I really get this. We get the cube root of 1 times cis. Now 180 over 3 is 60 degrees. And we'd say plus now 360 over 3 is 120 degrees, and we'd write k. Okay, so a few things I want to say about this. First of all, we know the cube root of 1. The cube root of 1 is just simply 1. And we also get CIS, and when you simplify this, we came out to be 60 degrees plus 120 degrees K. Furthermore, we could say, well, what do our K values need to be here? So we need to start at 0. We said we're going to go up to 1 less than the root we were taking. So in this case, we were taking the cube root. What we need to do is we need to find 3 separate roots. And of course, when you take the cube root, you should have 3 roots. So when we plug 0 in for K right here, you can see how when you always plug 0 in for K, you should always just get this first angle here. So we get 1 CIS 60 degrees. We also get this 1 CIS now 60 degrees plus 120 degrees times 1, which would be 180 degrees. So CIS 180 degrees. And then we also get 1 CIS. And then we'd say, well, 60 degrees plus 120 degrees times 2, which is 240, this would give us 300. And I apologize for the handwriting here. So the last thing I wanted to do is this. I wanted to graph the solutions, because one thing I kind of noticed in the last video was they all were evenly spaced around this system here. So we say 1 CIS 60 would be 1 unit. We call this R equals 1, and I'll say this is a 60 degree direction here. So we'd say 60 degrees. We'd say 1 CIS 180. I know where 180 is. 180 is right here, and I'll say that that's R equals 1 and 180 degree direction. And then 300, which would be 60 degrees shy of 360, but we'd say R equals 1 here as well. And then we have 300 degrees. What I want you to notice is that they're all evenly spaced about this plane. As a matter of fact, I'd say that the angle between them is 120 degrees, and that's how we're kind of connecting it to this number right there. Okay, so that's how you would find all roots of an equation just using roots of complex numbers. We'll just take the root that we're doing in the first place as a standard number, rewrite it into trig form, and we'll just use our theorem for finding roots. Cheers.